Organic chemistry is interested in carbon-based compounds. And in this topic, I'm going to review the fundamental concepts of general chemistry that we will need as we go and study organic chemistry. Atoms consist of protons, neutrons, and electrons. According to the IUPAC, atomic orbitals are one-electron wave functions obtained as a solution of the Schrödinger equation for an atom. It's a region in space about the nucleus where there is the highest probability of finding an electron. The S, P, D, and F are types of orbitals. Orbitals that have the same energy are degenerate. For example, there are 3 degenerate p orbitals that are oriented along the axis 90 degrees to each other. You know them as px if it's oriented along the x-axis, py if oriented along the y-axis, and pz if oriented along the z-axis. We can say the same thing for the 5 d orbitals and the 7 f orbitals. An electron configuration is the distribution of electrons in the orbitals of atoms or molecules. We know that hydrogen has an electron configuration of 1s1. For carbon, it has 6 electrons. They are distributed along the 1s orbital, 2s orbital, and 2p orbitals. Nitrogen has an electron configuration of 1s2, 2s2, 2p3 for its 7 electrons. Oxygen has this electron configuration, and neon has a closed shell configuration wherein its p orbitals are fully filled. Now for carbon, we can also make an orbital diagram such as this one, wherein your electrons are situated at 1s, 2s, and at 2p positions. Atoms tend to assume a noble gas configuration by transfer of electrons. Once electrons are transferred or accepted, the atoms will become charged, and here ionic bonding will occur. If atoms share their electrons, there will be covalent bonding. Now, ionic bonds form from electrostatic attraction between a cation, the positively charged species, and an anion, the negatively charged species. For example, elemental sodium here has an electron that can be transferred to chlorine. Chlorine only has 7 valence electrons, and once it's accepted the electron coming from sodium, it will have a full octet of electrons. This is a stable form of chlorine. Since it's accepted an electron, it will gain a charge and become -1. And sodium, losing 1 electron, will have a charge of +1. These 2 ions can form a crystal, and this crystal will have ionic bonding. Ionic bonds, or ionic bonding, is realized mostly in solids, wherein positive and the negative charges are right next to each other. Once they are mixed in solution, for example, if you add water to sodium chloride will separate into ions and they will be surrounded by solvent molecules. And in this case, there will no longer be an ionic bond. All ionic bonds has some covalent character. Within this crystal, there is sharing of electrons, however small that may be. We can estimate atoms that will form ionic bonds when they have more than 1.7 electronegativity difference, according to the Pauling scale. Now to covalent bonds. Covalent bonds are a region of high electron density between nuclei arising at least partly from sharing of electrons and give rise to an attractive force. The positively charged nucleus of the atoms tend to repel each other. The electrons tend to repel each other as well, but their mutual attraction to each other, the positive and the negative charges, and the right balance of attractive and repulsive forces will be able to create a net attractive force to form the covalent bond. Covalent bonds may arise from head-on overlap, and we call this the sigma bond. Here I have two p orbitals oriented along the same axis, and they will overlap to each other to form the sigma bond. A sigma bond is symmetric along the bond axis. Another type of covalent bond is called the pi bond. This is formed by sideways or lateral overlap of orbitals. In this case, I have a p orbital. They will overlap sideways and form this pi bond. Take note that in a pi bond, there are no pi electrons present along the plane perpendicular to the bond. Covalent bonds are represented by lines joining atoms. For example, here in acetic acid, carbons are connected to hydrogen and another carbon by a line, and this line represents 2 electrons. If 2 electrons are present on each line, then this carbon can have 8 electrons. This will satisfy the octet rule. Same way with this oxygen bonded to a hydrogen and another carbon. With 2 lone pairs equaling 4 electrons and 2 bonding pairs, oxygen can have an octet of electrons. Now we go to formal charge. Formal charge is a charge, positive or negative, on an individual atom. The sum of the formal charge gives the overall charge of the molecule or ion. Formal charge is equal to the number of valence electrons minus the number of bonds minus the number of unshared electrons. For example, I have here the nitrate ion. The formal charge of these 2 oxygens is equal to 6. That's the number of valence electrons of oxygen minus 1, the number of bonds found between oxygen and nitrogen, and the number of unshared electrons in oxygen. That's 1, 2, 3, 4, 5, 6. And you will get a negative 1. So this oxygen has a formal charge of negative 1. This oxygen has a formal charge of negative 1. For this nitrogen, the valence electron is 5. The number of bonds to nitrogen is 1 bond here, another, and 2 bonds here, for a total of 4. There is no lone pair found in nitrogen, so we have here 0. Overall, there's a formal charge of positive 1 in nitrogen. Now how about this oxygen? Again, it has a valence electron of 6, and there are 2 bonds for this electron to nitrogen. The number of lone pairs is 4, so we have a formal charge of 0 for that oxygen. If we take all the formal charges for this species, you will get 2 times negative 1 for the 2 oxygen and plus 1 for the nitrogen. We'll get an overall charge of negative 1 for the nitrate ion. We will encounter so many compounds in organic chemistry, and they are very complex molecules that are a combination of several atoms. For the case of the antidepressant fluoxetine, or more commonly known by the trade name Prozac, if the formal charge is 0 for an atom, and this excludes radicals, which we will talk about later. Carbon forms 4 covalent bonds. In these cases, carbon requires 4 bonds to form an octet of electrons. In here, there are a total of 4 bonds and 8 electrons overall. For hydrogen, it requires only 1 covalent bond. Hydrogen needs only 2 electrons to satisfy the helium configuration. Halogens usually form 1 covalent bond. For example, here is fluorine. The bond to carbon equates to 2 electrons, and so fluorine will have an octet. Oxygen forms 2 covalent bonds. Here, 2 bonds to oxygen plus 2 lone pairs will give it an octet of electron. And lastly, nitrogen forms 3 covalent bonds. 1 lone pair plus 3 bonds will give it an octet of electrons.